Hello. I encourage everyone downstairs to head back up, and we'll get going now with our next speaker, Dr. Christopher Werner of the Woodville Karst Plain project, and he's their science director, and I think this one's going to be a lot of fun. Come on up.
Thank you, Andy. My pleasure. Good morning, everyone. Hope everybody can hear me. Yes, sir. All right, so we're gonna change gears here. We're gonna talk about something that's very passionate for me, and I've spent a lot of time doing that. And I'm gonna point out some things that you probably don't know or haven't understand, but I'm trying to give a large overview into what we do and how it can impact a lot of different fields and a lot of different conservation type initiatives. So without further ado, we will take a look. I'm going to talk about what the Woodville Karst Plain project is, what our mission is, what we're trying to do. I'm going to talk a little bit about underwater cave survey and mapping. I'm going to talk about some theory of underwater cave genesis and how these things form. We're going to look at some underwater cave passages and the morphology or the shape, the cross-sectional shape of those. And we're going to relate that to some of the observations we see. Then we've heard a lot about sea level changes and climate changes. We're going to also talk about the influence of sea level and how that may have and probably did affect the underwater cave formation that we see in this area. And we'll talk about some implications, and I'll end with some forward exploration that we'll be working on and some forward research. So, what is the Woodville Karst Plain project? The first thing I want you to understand, we heard a lot about remote sensing. We heard a lot about satellites and imagery and other things. There is no way to determine with any current technology we have where underwater caves below our feet may be in the Floridan aquifer. The only way, we can't use ground penetrating radar or seismic, none of those tools work or can resolve these caverns. The only way to do that is to physically go there and explore them. Okay? So I want you to understand that first off. We've got no magic tools, no magic science that can tell us where these things are. All right? So the Woodville Karst Plain project, we got our name from the Woodville Karst Plain, and if you can see that, it's the shaded area south of Tallahassee, and it extends all the way, beyond the Osceola into this green part, which some of my geologist friends have recently subdivided in different ways. But Woodville in Leon County is the type locality for the Woodville Karst Plain. And so we are a 501c3 nonprofit organization. Our mission is to explore, survey, map, and document the underwater caves of the area. We look to educate people, and we're a very independent organization. We take no political sides. We'll work with anybody who's willing to listen to us, and we can provide data and access to many of the sites that we have permits with. We've conducted probably close to 9,000 plus dives over the course of 30 years, and that's about 400,000 plus hours underwater. Okay? We're a volunteer organization with about 75 different members, and along that we've got some researchers that are on the team that we work with consistently. We partner with scientists, researchers, resource managers, think your state parks, local parks, federal parks, refuges, individual landowners, and other citizens groups who think that we can help them in some way. So we're always willing to help out and be a platform for which people can use our information. We've got active special use permits from Wakulla Springs and the State Forest, We work with Florida Fish and Wildlife Commission, and we have a permit through them, and also at the national level. So the National Forest, the Appalachian National Forest, the St. Mark's Wildlife Refuge, and we also have special use permits with the U.S. Fish and Wildlife Service. So let's talk a little bit about cave survey and cave mapping. The picture you see here is the entrance to Wakulla Cave at Wakulla Springs if you were at the bottom looking out into the basin. If we look at that area south of Tallahassee, all the red lines are underwater caves that we have explored, surveyed, and mapped. And a lot of that history of exploration goes back well before our team had been found. But the yellow pins that you see are sinkholes or springs that we have access into the Floridan aquifer. And so we're going to talk about two specific areas just to kind of highlight that. The first is over at Natural Bridge, where the St. Mark's River Rise and St. Mark's Sink are, and then we're going to turn and look at the Wakulla Cave system and how we've recently extended some of the physical connections there between some of the other caves. So at the head of the St. Mark's River Rise, which you can see right there where that yellow pin is, this basically, the river rise there forms the lower part of the St. Mark's River as it flows to the Gulf Coast. Back in 2006, we worked with a private landowner. He wanted to sell his 55 acres to the state so that it would be conserved and protected. We worked with him. We explored more than 3 miles of passage. Connected 15 different sinkholes along his property and some of his neighbors' property. And to give you a feel for what that looks like in 3 dimensions, we're looking from the southwest to the northeast. And this little tube here is that guy right there. So you're looking this way at those, and you can see that all of these sinks and springs go down and they have caves, and the water flows there underground and then pops up. Average depth here in this area is somewhere between 90 and 100, 110 feet. We also have done extensive work on what is now called the Wakulla Cave system, where a lot of that water emanates from Wakulla Spring. But there are now We've been connecting over the years, so people that came before us had the ambition that a lot of this may be connected. We have picked up that mantle and kind of run with it in ways. What started out in the Leon Sinks Cave system up in this area here and connections, and what started with original exploration in Wakulla Springs area was finally connected in 2007. And then we are going to talk about an area within the silver box, or the yellow box, where we have now connected in another cave system that was separated from that. So if we blow up into that area, we will see Chip's Hole Cave with the entrance right over here. And a lot of you may be following this in the press about a developer who wanted to put a gas station down here almost directly over Chip's Hole Cave. This had been explored to a bit. We had done a lot of work in exploring this area here and thinking we could connect it, but over the course of 8-10 years, we still hadn't made a physical connection. So we did a exploration dye trace where we put a specific dye in. We traced it. We found it on the Turner Sink side, and then we pushed into a passage that we hadn't really looked at before, and we were able to connect it where that gold star is now coming up. And so that effort took us about 10 years in total, on and off, because of water clarity and visibility and things like that. But we were able to physically make that connection on January 7th earlier this year. And so that Wakulla Leon Sinks Cave system was about 38 miles long. And we connected it with the Chip's Hole Cave system, was 7 miles long. So we've now got an underwater cave that would rival Mammoth Cave in Kentucky if we could walk into it, but we can't. It's all underwater. It's almost 45 miles long at this point, okay? And it's still going. We've still got plenty of leads, lots of big passages down there to explore. We've got some pictures here in the upper right of one of our divers placing what we call a cave radio locator. This is a copper circle of wire, has a battery transmitter, puts a signal up through the rock that we can find on the surface. That's that middle picture in the bottom of my friend Steve finding that point on the top. And so when we connected it, we found that that ended up being, sorry about that, guys. That ended up being right in somebody's driveway in front of their house is where that connection was actually made. So this individual at Greenlee Acres in Wakulla County was surprised to know that they've got a cave right below their house. But one of the things we've been doing is compiling an extensive database. And so we've taken the historical records of the exploration over the past 50, 60, 70 years, all the way back to when they first got into Wakulla Cave system, and we're working, two gentlemen, Saltzman and Jenkins, were working with Stanley Olson to recover artifacts out of the mouth of the cave at the bottom of the basin in Wakulla Springs. So we've compiled now the exploration history. We put that in a database along with our surveys. So that's 50 years of cave survey. We've meticulously gone through and vetted that data for its accuracy and whatnot. We've done resurveys in places of that cave that we weren't comfortable was to the quality that we needed. And now with some modern techniques as far as GPS, satellite imagery, and whatnot, we've been able to provide, improve our accuracy of the geolocations of not only the sinks and springs, but along with that picture I showed you of the cave radio locates in places that are separated by long distances, there's always error in survey. And so those cave radio locations help us get much more accurate fixes between some of the natural openings that we see. The other thing that this database provides is scientific observations. So places we see changes in water quality, places we see changes in geology or sediment deposits, archaeology, whatnot. We can tie images as well as video to these stations within the database. And the best part of this is that it's built on an ArcGIS framework. So everything is geo-referenced. And that is available. We're working hard to kind of finish that up and get that rolled out, but this should be a fantastic resource for researchers and scientists going forward. So let's switch gears here a little bit and talk about how caves form, okay? Usually, isn't this a lovely shot of overhead Wakulla Springs when it was really clear? Which it hasn't been in quite some time, but this is what we hope to get it back to. Let's talk about cave formations. There's pretty much over the past 150 years been three primary theories for how caves form. The first one is called vadose entrenchment, and that is basically the way you would see a surface stream. It down cuts through some sediments into limestone rock, and then because of the chemical dissolution, the water will erode that limestone rock, and you will form incisions into the limestone along cracks and things like that. You usually end up getting quite a few different things along the water table, so the water falls down, and then it reaches the water table and comes out at a spring. And what you see in passage development is you usually see these vertical canyons, or you have these large pits or shafts where that's primarily like an underground waterfall. Okay, so this is water with a free surface. On the far other end member, you've got the deep phreatic. This was championed really in Europe in some of the alpine karst that we see over there, where you've got tilted formations and beds and lots of fracturing. And so water gets in, it takes a much more circuitous path along what we would call potentiometric lines that then you see water emerging, many years later at a spring. So development of the cave is well below the water table. A lot of times you'll get these large rooms that are connected by small little things in between. And so, where that water ends up mixing and meeting, you get a lot of dissolution in the large caves. What's probably most accurate for this area and is analogous also to a mammoth cave, if anybody has ever been there, is the water table formation cave theory. And so here, water gets down, it's enhanced as it goes through the surface sediments by organics. So you have lots of acidity and carbon dioxide that gets in there. It makes the water slightly acidic, and it gets into the water table in the limestone, and then it starts to dissolve away. And so you get these nice, really long horizontal passages like you see, but their morphology is much more circular and round like this, okay? Everybody, so make sure you paid attention here because we're gonna have a quiz later. Okay, so a lot of times these can be complicated because the water table is moved up and down. And a lot of karst scientists will talk about base level. In many cases, base level is caves that form in close proximity to a river. So that river would be base level. In the case here, in the Woodville Karst Plain, because the Gulf of Mexico is so close, our base level is sea level. But you can have modifications of these. So you can get phreatic tubes with all these small little things coming in because now you've lowered that potentiometric head at the conduit because that water is moving with a certain velocity and it's at less pressure, and so you get formation perpendicular to that. The other thing that you can get are these keyhole passages. So they started out in a way that they were just slightly under the water table forming there, and then that base level or that water table dropped. Okay? And so when you see this morphology, this means that then they started to downcut like a normal stream or like a normal vadose entrenchment that we would see later. And this is the cross-sectional figure that you get here. So that's how those guys form and what they look like. Okay, you ready for the quiz? All right, what do you think the cross-sectional passage is here in the Woodville Karst Plain on the top left? It's a tube, it is, but it's a modified phreatic tube in the top left. So that's really good. Right, modified phreatic passage up there. What about the one on the top right? That also looks like a phreatic tube with probably what you've got is a small bedding plane here where that originated with, but you can see that's definitely a phreatic passage. What about the lower left? And for Andy, I'll point out the bottom of this is our quote unquote girthite in the dark there. So what do you think that is? Well, you've got the tube on the top, but then you've downcut that. So that's one of our keyhole passages, right? There you go, Vaughn gun. Yeah, yeah, exactly. So, and what about the one on the bottom right? Okay, we've got kind of that same thing. You can see it back there. You've got the phreatic tube, and then you've cut down this little canyon. So that also is a keyhole passage, okay? So that means that in places here, right, in these keyhole passages, the free surface of the water had to be below this because it's down cutting in a trench. You can see this on the Oscilla if you walk that trail. There are these really nice canyons that the Oscilla flows through in places. Same thing. So now let's look at some observations, both of morphology and the passages from that extensive database that I was talking about before. Those were at Wakulla Springs. Okay, so what do we see? Let's talk about keyhole passages. We've got two really good observations in two places within the cave. And I'm sorry that red may be a little bit, but just north of Cheryl Sink, we've got an area where we've got a tube with a down cutting, and that's at 190 feet below the water table. So we know base level had to be there to form that. We don't know any other way that those can form, okay? The same thing in the southern part of the system, really beautiful, just north of Turner Sink, in this beautiful spring passage at a depth of 215 feet or 65 meters below the water table. We've got exactly that same thing with your keyhole passage cross section, okay? So that's quite deep. But we know from the sea level record that we've got that things have been lower, okay? So one of the other morphologies that we talked about in Vados entrenchment was these large shafts, vertical pits almost, or these underground waterfalls. Well, if we look at the survey data and we look at that passages, we can find examples of those. And so to read these, we've got a pit here at the confluence of two large passages just upstream of that, where we go from a depth of 140 feet to 210 feet. Okay, so that was an underground waterfall. We've got those throughout the northern part of the Wakulla Cave system. Like, remember this guy over here at Sullivan Sink? He goes from 70 to about 220. We even see these farther south. So if we go down to US 98, close to, I think this is Ray Winkle Road, we've got a few underwater caves we've surveyed here, but they've also got these very large vertical pits. There's no way to, you ever seen the Bahama blue holes? That's what these things look like. You come into the top of them, and then there's giant holes, and they go down, and at the bottom, there's continuing cave. So the only way to form these is if they have a free surface of water, okay? So now let's look at the underwater passage and how that's distributed throughout parts of the Wakulla Cave system. The first thing we're going to talk about is the Chips Hole Cave system. If we look at the depth of where those passages are formed and how much passage is formed there, right? So we're talking about depth on the ordinate and on the abscissa. We've got a total length of cave passage at that depth. This is what that distribution looks like. The different lines are when we sum them over 1, 2, 3 meters, do a running average, those things like that. But we sum them because sometimes we're surveying the line that's at the top of the passage, sometimes it's on the bottom of the passage, sometimes it's in the middle. So to kind of get a more accurate read here of where this is developed, we're seeing two primary places, minus 21 meters and minus 36 meters below the water table. If we look at Leon Sinks North, we're seeing a different distribution, but still a distribution where we're seeing passages form primarily at minus 18 meters, minus 33, and minus 57 meters of depth below the water table. We can go to the southern part of the Wakulla Cave system, what we usually refer to as Leon Sink South, and there we see a much different distribution where a lot of the caves there are all at much more extreme depths, 86 meters on average, okay? If we stack those all up and put all those together and look at the entirety of the cave system together, what we see is essentially 4 primary development levels of where most of the passage that we have explored is. Now this is probably, we haven't explored all the underwater caves. So this is a population, this is a subset of a larger population, but this gives us some insight. And during a master's thesis back in the late 90s, I had looked at this, even though our data sets are nothing like they are now, in a much more crude way. But you see these preferential development at various depths. And so the question becomes, what does that mean and why did these caves form like that, right? The other thing I want to point out Remember that Sullivan sink? I told you to remember that pit. In the upper part of this pit, we have these beautiful sediment deposits in what looks like, kind of in these incised valleys that either these were pools eroded later, and they had deposited sediments there and eroded later, or these things were stacked up when you were at much higher, much lower water tables at that. But you can see on the close-up, that's centimeters on the left, inches on the right. You can see lots of stratification of these sediment deposits, and even in here, you see almost laminae that have formed. So in this part of the cave, there are 3 of these sections. This is the only one that we were able to photograph prior to the conference. But each of these is about close to about a meter of thickness. So we have not done any studies on there. We see these deposits like this throughout the cave system. So I'm hoping some of my scientist colleagues, bells are going off about, what a unique resource this could be to sample later on. So let's talk about the influence of sea level. We've heard a lot about that over the past day and a half, and here is one of the much more modern sea level stacks. A stack is a compendium of several different sea level cores, either from cores or coral ridges that have been dated and looked at. Most of these are from foraminifera, looking at delta O18 isotopes and the frequency with that. What I like about the stacks is that the researchers have gone through meticulously to kind of align these up, and while maybe not perfect here for the northern Gulf of Mexico in the Big Bend area, it gives us some insight into where sea level was at different periods. So the scale goes out to 798,000 years, almost 800,000 years. And so what we find is, or what we surmise is, if sea level stayed in certain places for a long period of time, and we would say, well, here, you look here, sea level was fairly constant through, a few thousand years there, maybe up here, maybe there, right? Can we see any signature of that? And so if we look at the frequency or the duration in 1,000-year intervals of how sea level looked, you can say, well, I really don't see anything. But when you dig into the data, you realize that the resolution of some of these things isn't that great. And so if we then say, okay, the resolution could be off a few meters. So maybe we start to stack these on a 2-meter interval or a 3-meter interval, or lo and behold, a 4-meter interval. We start to see that sea level duration at a certain height has actually, we start to see these things. So that's more than 30,000 years. Minus 14, minus 32, minus 50, minus 86. Oh boy, doesn't that sound a lot like the passage distribution we saw at Wakulla Cave system? And lo and behold, it probably is. So what are some of those implications? While not a perfect correlation, earlier work suggested we were getting correlation coefficients anywhere from 0.55 to 0.68. We haven't yet run those. We're still vetting some of the database, but I did want to put this up for you guys. If I did this over a 1-meter interval and didn't move anything, didn't account for the height of the water table or whatnot, we're running here about correlations of about 0.56. So there's something to investigate here. More work needs to be done, but there is some relationship here that we should not forget about. Okay, so what does that all mean? Art Palmer had done a ton of really great work at Mammoth Cave relating what were river terraces of the Green River, his base level, to passage development through time. And so, you get the river down cutting, and you get the water coming in, dissolving out these pits and these long horizontal passages, and as time goes on, the river begins to down cut more, and you get these levels of passage development, and then at some point, the river came up a little bit and probably sedimented some of the more subterranean aqueous-filled, water-filled passages down here. But we see something very similar in the Woodville Karst Plain from this. So there's strong evidence here that the geomorphic features are analogous to sea levels being much, much lower, because we don't know how else we would form some of those geomorphologies in the passages. The other thing that's interesting here is that the water tables do appear to be correlated to sea level. And because of the hydraulic conductivity and the transmissivity of those carbonates, those limestones of the St. Mark Swanee that we see here in the Woodville Karst Plain, those are probably well correlated. And because they're so high, those sea levels in the water table have also dropped probably to the same magnitude. So we can kind of move forward and say, look, there is some relationship between sea level heights and passage development, where we're seeing that in the distribution, and that probably that water table theory of cave formation is pretty close. It may not explain everything, but it gets us within the ballpark. And then you've probably had modification of those caves by vadose entrenchment because sea level has fluctuated so much. So you've gone through this period in several periods of time, and I think we could probably maybe able to put an upper bound on when some of these caves first formed based on that 800,000 record, 800,000 year sea level record. And likely, we're probably seeing a lot of the springs and sinks that are now submerged off the coast that others have talked about. Those have, some of them are still active. Many of them are probably have been experienced sediment fill to the point where they don't flow as much anymore. So they're probably out there, but getting in them would be nearly impossible at current. So we think we can probably constrain these things with a combination of looking at the data set, running some more analysis on that, and some higher powered statistics. I'm happy for anybody that wants to help with that. But we also think we can constrain a lot of this based on some of those sediment deposits and what may be there. So if you think about where those sediment deposits came, they came from the land surface, streams that were running in, and then we're dumping into there. And that would capture anything. So, your pollens, your freshwater critters, all kinds of things are probably within some of those records, and they're widespread. So that was just one example. Okay, to kind of finish up, I'm going to talk about where we're exploring now and some of the future research. Okay, so everybody knows this, but within the Woodville Karst Plain, those are primarily the caves that we have spent some time on. But our first priority is getting back to the refuge. We've made a breakthrough in the past year or two in Shepherd Spring, and so we think we have the ability to run that north, and it's getting close, even though the scale here is quite a bit from the southern end of Wakulla Cave. This may be one place where we could see a connection to the south. The other place we could see that connection is probably at Spring Creek, and we believe Spring Creek is probably related to these caves that we see here on US 98, which we had pointed out before. So that's another priority for the team as far as exploration goes. And then we're going to get back to the St. Mark's River Rise and Natural Bridge area. That itself has a lot of really interesting things, but we need one of those La Nina periods of time where things are really dry, people's grass is dying, the crops aren't any good, because during droughts, things clear up for us and we have the visibility that we need to get into some of these more river-influenced tannic systems. And then finally, we're hoping we can get into some place like the Nuttall Rise. We think that's got a heck of a lot of similarity to the Natural Bridge St. Mark system. And so would love to get in there. So we're working actively to try and negotiate our way in there, because we think that could benefit a lot of folks in the room. As far as research priorities, we are working to finalize that cave survey and historical exploration database. When you're talking about 70 years of history, we want to get that right. The other thing is prioritizing areas that we know the survey is not up to the quality standard it needs to be. And we're also incorporating a lot of the scientific observations. That's a manpower thing. That just takes time. The other thing is we're going to continue to work on the influence of sea level with the cave passage formation and development, and we're going to look at correlations, timing, and time frames of formation. And then the other thing I wanted to point out is we've had a lot of people come to us and say, hey, can you do photogrammetry, or can you do some side scan sonar and whatnot? We've now been working with a company, and we have now in our diver propulsion vehicles, this thing on the top is essentially a equipment apparatus that has navigation, it has side scan sonar capability, so we can fly through the cave and get bottom profiles via a side scan sonar. We can also look at a photogrammetry. So in upstream Sullivan, we had done a nice photogrammetry. This is probably about 1,000 meters across, or 1 kilometer across. This is the entrance to one of those rooms. This is the exit, and you fly through. So in places, this is 30 meters high, just tremendous cave. But we can then suck that into a 3D modeling program and fly you guys through. So that's all work in progress as far as research priorities. So that's pretty much all I had. I did want to put up my references, just for those that wanted to go check my work. And we want to thank all the people who support our team and whatnot. There's quite a few, and we've made some really good friends. So like I said, we're willing to work with anybody. You can see us on our website or on our Facebook page, and if you want to see some videos of how we go about surveying, that's up on the Black Abyss Productions YouTube site. This one will tell you about how we survey and map, give you a little tutorial. It's about 5 minutes. If you want to see more about that most recent connection between Turner, Sink, and Chips Hole, there's a video about that. And just as a shameless plug, next year we'll have a documentary about that and its influence on the conservation of the area coming out next year. And so there's a lot of YouTube videos up there with some trailers to hopefully get you guys excited about that coming out. Ready for questions?
Other than Wakulla Springs, have you found any archaeological material?